Well, hello everybody. Thank you very much for joining us today. This is Paul Taubman with 9.Connects. Today's webinar is a deep dive on inductors. And to just give you a little preview, I had an opportunity to check out this session yesterday when Jeff did a practice run, and you are truly going to drink from the proverbial fire hydrant today. So this will be presented by my colleague Jeff Condit, who is a senior engineer here at 9.Connects. And without a further ado, let me welcome Jeff Condit.
Good morning, everyone. This is Jeff Condit with 9.Connects, and I'd like to talk today about inductors. And so we'll start with a little bit of terminology. There's a lot to go through, so I'm going to kind of keep booking it through here. First of all, there's three terms I'd like to talk about: inductor, transformer, and choke. An inductor is specifically a device designed to store energy to and from a magnetic field, and is typically characterized by a value of inductance in henries. Let me move something that's in my way here. Okay, sorry about that. An inductor is specifically designed to store a bunch of energy and is characterized in henries. A transformer is not. It's designed to pass energy through it, but to store essentially none of it, and is characterized by a voltage or a turns ratio, and hence also can change impedance. A choke, on the other hand, is designed, it's like an inductor. It will store some energy, but its primary purpose is to absorb the energy. It's designed to be lossy. And so those are some of the terms that we don't have. Over the years, over the recent years, the term choke has tended to become more synonymous with inductors, but it really means a lossy inductor for the purpose of choking off certain signals you don't want. Okay, symbology. We're going to be very quick. Some people use just a rectangle that comes from Europe, but the coil typically, historically, is drawn as a set of arcs. And there's a bunch of other information that's supposed to be conveyed with the symbology if you want people to understand what it's doing. One of the first ones is there are core materials. For laminations, they typically use a set of parallel lines over the coils to indicate the laminations, iron laminations. Then they found they could powder it up and center it into a block and make it into a powdered iron core. That's a set of dots over the inductor. And then you end up with ferrites. And for ferrites, they use dashed lines over the inductor. So throughout transformers, inductors, and chokes, you'll tend to see that symbology. It tells you something about what's there. You'll also see that if it's going to be adjustable, there will be an arrow through it, usually at like a 45-degree angle or something approximately like that. If it's adjustable, but it's not something that the user adjusts at the time that they're operating the equipment, it's something that's, say, adjusted in calibration, then it would instead use like a T-pin, almost like a nail being driven through it to hammer it down at a particular value of inductance, okay? And then, of course, you can have taps, and the taps can either be fixed, in which case they're a little wire coming off of a couple of the points of the arcs, or it's an arrow coming off of a couple of the points of the arc. The same thing is true for transformers. Generally, all the same information applies. Note that a variac can be drawn with one coil because it is a single winding. However, it is tapped, okay, and it is actually a transformer because it is designed not to store lots of energy. It's designed to transfer it through. On the right, you'll see transformers designed for power. It's customary to show the pinouts of that as the leads coming off from the transformer. Usually the primaries on the left, secondaries on the right. The core is also indicated, and the voltages of the windings are also indicated in each coil so that you can tell what it nominally is supposed to do. All right. Chokes. Chokes are intentionally lossy inductors. Basically, for their symbols, they look very much like a regular inductor. However, they will oftentimes say choke or RFC, standing for radio frequency choke, near them. They may specify impedance values at frequencies and be be indicated as a coil wound over a resistor, either a block resistor or a triangular shaped resistor. Sometimes they use the symbol shown there. I personally have never seen that used, but the main usage example, again, for a choke is where you're trying to block EMI, say at the power input. Okay. Historically, inductors were used many, many decades ago because they were very easy to make. You just take a piece of wire, wind it around a pencil or a piece of pipe, and you're done. You can just buy a coil from the store and stick it in if you wanted, as long as it gave you the right value. And they went on to make some very high-powered ones that you could actually rotate, and they'd have roller taps on it for adjusting things like high-powered transformers. You know, 20 kilowatt. How do you tune a 20 kilowatt transmitter? Well, you have to have some kind of tuning element, and they'd oftentimes tune the inductor. It was easier than tuning the capacitors in many cases. One of the things that happened is okay, let me go down. It turns out that capacitors were really hard to make in the early days. They tried to wind up a bunch of foil and paper and dip it in wax. It took a bunch of time. Eventually, mass production took over, and capacitors became very easy to make. And so now, capacitors used preferentially over inductors. But the inductors have always been there, and they're very stable, very simple devices. So let's talk. What is an inductor? Basically, any conductor is an inductor. So let's elaborate on that. How is it that a conductor is an inductor? First, if you see the wire going down through on the left, you'll see that there's magnetic flux around it, and that obeys the right-hand rule, as shown in the middle, in terms of the direction of the flux with respect to the direction of the current. It's also shown on the right-hand side. Because there's a field out there, something is affecting things, causing them to line up. There's energy in that field, and that's because there's permeability even in free space. If you put a current through a wire, it makes a field, and it takes some amount of current and some amount of force to do that. Since there's energy stored, there is an inductance, because E equals 1/2 L naught I squared. If you have E and you have the I, well, then you have to have an inductance. There's always an inductance. So any conductor is an inductor. Now let's say you had something twice as long. Well, each piece is going to have the field that it normally would have. Therefore, it will have the inductance it normally would. And you're going to find out that you have twice the voltage if you were going to play with it with a changing current. And it turns out that the inductances add. Inductance is proportional to the length of the wire. So we normally in a wire talk about the inductance per unit length, and it's equal to twice the energy divided by the current squared. Even no conductor is an inductor. That should be a strange one for you to think about, but let's suppose you have no conductor. Take a cathode ray tube, put a high voltage to it, and you emit electrons, and they fly over and hit the anode. All right, you have a current flowing. Guess what? That creates a magnetic field. In the magnetic field, it's storing energy. There's a current, there's a magnetic field, therefore there is an inductance to it. Hence, even no conductor is an inductor. So we're kind of expanding a little bit what we've seen. Henry A. Rowland, a long time back, he was a physicist, demonstrated by taking a fan motor and putting a phonograph record on it that he could take a piece of wool cloth and charge it up. And then he took a compass and showed the direction of the magnetic field and showed that it did indeed create a magnetic field. Well, how is that? It's because the disc itself has charges. In this case, they're fixed on the plastic. They can't move with respect to the plastic, but the fan motor can spin them around. If it's spinning them around, it's making a circular current. And if it's making a circular current, it's like a loop of a coil, and it creates a magnetic field just the same. So just a couple things of interest. So what happens when you take a wire and make a loop and stick it through a plane? Well, the current goes up on one side and creates a magnetic field, say with the current going through the center because your thumb is up. On the other side, the current loops around and is going down, and if you use the same right-hand rule, you find the current still goes through the center. Okay, so the current's going through the center and then is returning around the outside. You can make a whole bunch of loops of wire and form a classic solenoid coil. And then through there, you'll find that indeed all of the magnetic fields align in the center, and they go through and form a very strong field through the middle of the coil, and then they come out the end and go around back out the outside in the opposite direction, forming complete loops. What about between the wires? Well, between the wires, since the current is going in the same direction between each turn, one turn will have the field going down, the other will be going up. And hence there's they cancel. There's almost no flux in between the turns. Therefore, if you were going to ask, well, where is the magnetic field? Is it stored right around the wires? The answer is generally no, unless the turns are pretty far apart. Then you start to get a little bit stored there. And by the right-hand rule, you can also use the rule that you can put your thumb in the direction of the North Pole, and your fingers in the direction the current will be going around the windings. It's another corollary to the right-hand rule. Okay, but what happens if you need a lot of inductance? And an air core inductor could get huge. So is there a way to multiply inductance? Well, the answer is yes. The answer is in finding magnetic materials with a property called relative permeability. All right, to explain this, let's talk just for a moment about magnetic domains. This is a huge subject, so I'm going to abbreviate it, and so it'll be slightly incorrect, but not much. So first of all, magnetic fields arise from properties of electrons and to a lesser degree those of atoms. And so when you have a magnetic material, you have a whole bunch of potential little pointers that can point in any direction with a magnetic field. In the little depiction A, you see that they're pretty much pointed in all sorts of little directions. What really happens is if they all would want to line up, if one could coerce another one to lining up, they would all go in the same direction. But if they all went in the same direction, the field lines would go straight from one end of, say, a bar to the other end, but then they'd all have to go out through space, and it takes a ton of energy to magnetize space that much. Whereas the magnetic material, it just goes where it wants to. It likes to do that. So instead, it turns out that they form their own little miniature loops inside where it kind of goes around in circles. And these are little domains where the magnetic field is happy in and of itself. Now you come along in B and put a strong magnet on it, and it'll automatically force all of those to align. They want to align, and now you're overcoming the energy outside that it takes to complete the loops. So they're happy to all align. Okay, but what happens if you remove the external field? Well, now you still have to have all that energy, so it's going to tend to collapse to, again, by what's in C. Now, they may tend to be still a little more aligned than they were originally after you remove the magnetic field, but they will be less aligned. And we'll see that when we look at the BH loops a little bit later on. That's one of the things that's going on that is happening. Let's take a look at it in more detail. They have found ways to actually map out the magnetic domains. Typically, they use microwaves in a very fine point, and they scan it over a particular material. Magnetic material has grain boundaries, but it also has magnetic domains. They're different things. The grain boundaries have to do with the direction of the molecular crystal arrangement, and the magnetic domains are, of course, which way the magnetic fields are polarized. When you polarize it, when you look at a material, you're going to find there's areas where it's where you see a north pole, areas which you see a south pole, and in the way that they've colored it from their diagrams, they tend to be adjacent to each other. You have an up is light colored and a down is dark colored. If you have a magnet and you've kind of run it to where it's sort of polarized one way, and then you cut it along the direction of polarization, you'll tend to see that there are layers of north and south. If you cut it crosswise, you'll tend to see that it's more of a squiggly pattern. And these are actual images of magnetic fields that they have taken. So, permeability. What about permeability? This test says, well, okay, it's the ratio of the total magnetic field that we're trying to get to, which has a symbol B, based on that arises as a result of applying some external magnetic field we call H. It's actually usually rated in things like ampere turns. If we have more turns or more amps, we're forcing harder, and so we get more residual flux. In free space, where there is absolutely nothing, if you apply some H, you get some B. And that it has to do with the permeability of free space, mu naught. Mu is the symbol for permeability, and it's defined as being 4 pi times 10 to the minus 7 henries per meter. That's a universal standard. It's kind of part of the definition of the unit system. So, relative relative permeability of various materials is different. It's how much better a material reacts than a vacuum would. For example, the relative permeability of a vacuum is mu sub r equals 1. That's because that's what it is. You haven't got anything else. So the B field is equal to the response of space, mu naught, times the response of a magnetic material, mu r, times how hard you're forcing them in ampere turns. Okay, so that's typically the formula for magnetic induction. What we want to do is find a material sometimes to get the inductance up. Maybe not that's too high, but to some level. Here's a table of various values. You can see air is almost non-magnetic at all. There's a tiny little bit. I think it arises from the oxygen in the air, but it's very, very weak. Carbon steel, we can stick a magnet on. It sticks really well, and that's got a permeability of 100, so it works pretty well as just an old cheesy carbon steel. Ferrite, where they make manganese and zinc, is about 640. When they get to electrical steel, which is a much better grade, it's about 4,000. 99.8% pure iron is 5,000. Permalloy, which is used in all sorts of high-end magnetics, is 8,000. Mu metal, which is used for shielding, is about 20,000. And if you use 99.95% pure iron annealed in hydrogen, you can get it up to 200,000. And Met Glass is a company who makes these high permeability materials, has actually come out with a 2714A annealed product that is 1 million, and that is really phenomenal. So that's a very, very high relative permeability. You put a little tiny current near it, and it just forms a huge magnetic field in response. Okay, the real question, though, is when you're trying to ask which material to use is how strongly or how completely do you need to conduct the magnetic field around some particular path. Okay, let's digress for a moment onto the duality of inductors and capacitors. First, you can have voltages, and voltages are very much like currents. Inductance and capacitance are both measures of stored energy and parameters like that. You could have also E fields versus B fields. So, generally, there is a complete duality in the sets of equations between these, and most people are used to working on the capacitor side. We understand there's a capacitor, there's plates, there's an electric field, and it develops a voltage. You squirt some current into it, and I equals C dV dt. Far fewer people are familiar with the duality of inductors, but it really turns out that that they're very similar, and so you really need to find you need to understand that. It implies that you can do the same things with currents, current sources, magnetic fields, and inductors that you can using voltage sources, electric fields, and capacitors. We've kind of lost sight of that over the years, and many engineers feel uncomfortable with it because, number one, it was typically not given equal coverage in universities. Two, it's rarely presented in data sheets and technical materials. Three, it's far more components have been developed for the voltage, electric field, capacitance side of things than for the inductor side of things. And as a result, there's just generally a lot less familiarity with it. That doesn't mean it's any harder. A quick example, if we take a voltage and stick it across an inductor, the current ramps up. That's great. If we've taken a current source and put it across a capacitor, well, then the voltage ramps up. So we can ramp up current and make B fields, or we can ramp up voltages and create E fields. There's a complete analogy. Let's digress to some cores a little bit. In the beginning, they didn't have cores. They just wound things around. They were either air core or they wound them around a scrap piece of iron that they found, and they generally did not have controlled magnetic paths. When engineering first got on the scene a century ago, they needed something, and they found that they had rolled out iron laminations, and they could stamp them out in patterns, so they came up with the EI laminations you see in the upper right. Typically, they would stamp an E and an I, and they would stack these all up to form a core. And the holes in there, they'd actually wind a coil around a square bar, and then they'd dip it in varnish, or else they would sometimes use a form for it, and then put it in there, and they'd come up with a pretty great inductor. When they tried to do a transformer, it didn't work so well because there was too large a gap. For an inductor, you want a gap, and where the stack of I's touch the stack of E's, it doesn't make a good magnetic contact. Matter of fact, to increase the inductance or decrease the inductance to store the energy, to increase the energy storage, they'd oftentimes put a piece of fish paper between the E's and the I's so that there would be a known and controlled gap. But for transformers, they needed to get rid of that. So they started alternating the EI laminations on each layer as they put it together, and that made some very, very good transformers, and that's what you see in a lot of big power transformers today. They also decided that they could wrap those around a square bar, as seen in the middle on the left, and form some loops with a square center. They'd cut them in two, and then they had C cores. Or they would wrap them around they'd take the C cores and put three together and form tape-wound EE cores, as shown in the lower left. Or they'd take a round bar and wrap it around there and form tape-wound toroidal transformers. And those were really useful too, but it turns out wasn't until about the 1950s that they came up with a machine that could actually wind toroids, and it was just too cost prohibitive to try to do it by hand. But now they can wind them with machine, and it's not so bad. Later, down in the lower right, they found they could powder up the iron, they could stick it, cram it in a mold, and sinter it, and it would stick together, and then they could form oddball shapes. So they made their E-cores that way, and other shapes, E's, I's, C's, everything else, as powdered iron. They also found later that they could come up with ferrites, and they started making cores like the pot core shown right in the center. They have an advantage that you can put you can wind a circular bobbin, which is very easy to do, stick it in the middle, put the pot cores together, and it's magnetically shielded all the way around, so there's very little fringing flux coming out of a pot core. They can also they could also make various other shapes that were better for packing on small boards, such as squarish type pot cores. Okay, energy is primarily stored in the gaps, not in the magnetic fields. I'll say it again. Energy is primarily stored in the gaps, not in the magnetic fields. Magnetic materials are there to make strong fields easy. Very easy to come up, but to store a lot of energy, you have to do work. Energy is power times time. Power is volts times current. So let's imagine a perfect magnetic material, something with infinite permeability. Then if the relative permeability is infinity, then the inductance tends to infinity, and applying a voltage to it causes nothing to flow. I mean, in the equation I equals 1 over L integral of V dt, if L goes to infinity, well, then you end up with 0 for 1 over L. Hence, the current will never go up. So power flow into or out of an inductor in such a case with high permeability is very close to 0. Thus, negligible energy is stored. Negligible energy is stored. It's not good for power conversion. It's not good for storing and getting energy out. Permeabilities are typically so high that gaps are needed to facilitate energy storage. Now remember, I'm talking that this is bad for inductors that are intended to store energy, but not for transformers. Transformers do not store energy by definition. You try not to store energy in a typical transformer. Transformer does not really mean that it has more than one winding on it. It basically means that it's transforming the energy and not storing it as an inductor. So if you want to have a transformer, you can have very high permeabilities and not have much inductive current. That's a good thing. But for inductors, you need a gap. Now that gap can be distributed, or it can be put in at a specific place. We'll touch a little bit more base on that in a moment. What about imperfect inductors? Well, inductors have resistance first. They're made out of wire. Wire has resistance. And so that resistance means that unless it's superconducting in some way, which I don't think copper becomes superconducting, you're going to have losses in there, and that loss turns into heat. So as there is current flowing in the winding, there are I squared R losses, and it goes into heat. Now this can be very significant in the case where you have a high inductance. When you need a high inductance, as shown below, it's when you need a lot of turns to make it, and you do that because either it has to support a high voltage for a long time, or you can do it because you have a very low frequency. So it can be a low voltage for a very long time, or it can be a very high voltage for a short time. So high inductances have lots of fine wire. Lots of fine wire that's a lot of length of something that's small in diameter, and the resistance goes up. There's another factor that needs to be considered, especially for the big fat turns, and that's the skin effect. What happens, this is something that happens on AC, high-frequency AC signals. As current flows through a wire, it basically causes a magnetic field around the wire. In particular, if current is flowing in the middle of the wire, and it will cause a magnetic field circularly, as shown like the blue circles, around the wire. And for the currents inside, some of that magnetic field will be inside the wire instead of outside the wire. Now, what happens if it's a changing flux? According to Faraday's law, if you have a changing flux, those blue circles are changing in intensity, and that induces another current, a circular current, around that area of change. And that is ordered. If you follow the arrows and the right-hand rule, you'll see that those are little red circles where it's going in the same direction as current flow on the outside of the wire, and it's going in the reverse direction on the inside, closer to the center of the wire. That, when these all add by superposition, it means that it looks like the current is flowing down the outside and very little is flowing down the inside. And you can see that that's called eddy currents, and it's induced not by core materials. It's induced by the eddy currents are induced by the rate of change of current in the wire in the internal core of the wire. There's a chart over on the right shows how the impedance falls off with frequency, and you can see the copper colored trace and the silver colored trace are for copper and aluminum, and they're up pretty high, but there's other traces down low. Note that the one at the very bottom that's kind of a dark gray is for an iron nickel. Iron nickel is a very magnetic material. Why would it be so bad? It's bad because it's so magnetic. And so when these changing fields occur, the H field, it creates a lot of additional B field, which causes the little circulating currents to be much further, much tighter and stronger right near the outside. Okay. Imperfect inductors. They are imperfect. The first thing let's talk about is capacitance. Between windings, between individual wires, there's capacitance. Between windings even further away, there's capacitance. There's windings, there's capacitance down to whatever you're holding it on. There's capacitance everywhere. How do you decrease the capacitance? Well, you can move things apart, or you can make things cross at right angles or do other special games. There are some winding methods that significantly improve this, like those shown down at the bottom. First, there is on the right, you'll see a classic RF choke, which stands for radio frequency choke, which means they can use it at radio frequencies because it has little enough capacitance. How do they do that? Well, first, if you look at the windings carefully, you'll see they're sort of cross-hatched because they're winding back and forth and back and forth and back and forth on it to build up each stack. Then the stacks are separated with a distance. All that action reduces the winding to winding capacitance, and thus you add up a lot of inductance and you keep the capacitance low, and therefore you can make it have a self-resonant frequency high enough that it will still work. Second, in the one in the middle is just a regular simple coil, but it's been stretched apart so that there's an air gap between all the turns. That decreases the inductance. Similarly, the one on the left is a plate type winding, a flat type winding, planar winding, but it uses an odd number of little things that stick out, sort of like tongue depressors, and they weave in and out between there. Since there's an odd number each layer, the wires are crossing. There's none that are laying parallel to each other, at least not on adjacent turns, and as a result, the self-resonant frequency goes way up because the inductance goes down. As we can see for the graph on the right, an E-core with a foil inductor, E-core has a square flat center. You wind it with foil, and you're actually putting like a foil layer on each other. The wire is a foil. There's lots of flat plate capacitance between turns of a foil, and hence it has a lot of capacitance. Hence the self-resonant frequency will be low. If you do the same thing with solid wire, there's more air between round wires than there are for flat wires, and hence it goes up quite a bit in the blue trace. The green one is a toroidal inductor, and it's even better, and the reason it's even better is because you wind it and it's really tight in the center of the core, but as it goes to the outside, because the outside's a larger diameter, it has a larger perimeter but the same number of turns, there's gap between there at the outside. So the toroidal structure is actually even better when it comes to that. Let's talk about other factors in imperfect inductors. Magnetic materials, they have hysteresis. Hysteresis means that when you apply a current to something by moving to the right of the curve, the lines go up. Eventually, it tapers over, and then you go to the left. The current changes and goes the other way. Say a switching transformer, back and forth. It goes up and to the right, and then it goes over and down to the left, and then it goes back and up to the right. And every time it's tracing out, real inductor traces out a curve. That's because there is some hysteresis in there, that the going up and the coming down do not occur on one exact line. They're separated, and as a result, energy gets stored in there. Magnetic materials also saturate. If you look at the top, it doesn't keep going up and down and the same as it does in the middle. It actually flattens out at the top and flattens out at the bottom. That's where you've pushed the magnetic material to the max it can do, and now you just have a coil of wire that's in essence working in air. And it isn't a slope of 0, it's actually a slope of 1. Relative permeability equal to 1. That's the slope. So it does have some, but it's very low compared to the tens of thousands that you would see in terms of if it has a magnetic material. Eddy currents, when the magnetic fields inside the core itself are changing, they are creating little currents that flow because it's also electrically conductive. And that will then the core material typically has some resistance in it, like iron cores, iron has some resistance, and those currents as they flow around will actually lose energy to these eddy currents and cause it to heat. There's also incomplete flux containment. Some flux comes out of the core. If it's a really good material, it's very low. However, if you put a gap in there, you'll find that when you put a gap in the a core, there's a little fringing at the flux. We'll see another slide of that later. And also magnetic materials can only go up to a certain temperature. If they get too hot, they stop becoming magnetic, and therefore you have a problem in it just becomes like it's air. It's not there. So you can't let them get too hot. Magnetostriction is another thing in large power transformers such as iron core. The iron gets changes slightly in size as it has magnetic flux or not, and as a result, you put a big power through it, and you'll hear a power transformer hum. I'm sure you've heard that, okay? And there are also, at high speeds, there are skin effects that come into play. All right, let's understand a simple BH loop. We already have talked a little bit about this, so I'll make it very fast. H is the horizontal. It's the magnetizing force. It has to do with ampere turns, and it basically moves left-right on the curve. B is the vertical axis, and it's measured in Teslas or Oersteds, and it's the resulting magnetic flux. Because there's a magnetic material, it'll have a steep slope right in the middle, and when it saturates, it'll be flatter. The slope the saturation reduces the relative permeability, reducing the slope when you get to high levels of magnetic flux. As you get towards saturation, more and more of the total flux starts to extend outside of the core, which is the fringing loss that we see. So if you're worried about that EMI, don't drive it that hard. This uncontained flux can couple to other things causing EMI, and it can also cause heating. So it's good to stay away from the saturating regions, stay in the central area. There are a few uses where you have to use saturation to accomplish a goal, but those are specialty and I won't talk about them here. Okay, typically the H field, the magnetizing force, is rated, it's amperes times turns divided by meters. The permeability of free space is 1.257 times 10 to the minus 6 henries per meter. And mu sub R is a multiplier, we've talked about that. And the resulting flux is the B field, and the B field is basically mu naught times mu R times H, as shown in the equations. And we'll go quickly through this for the sake of time. The slope of the curve is the net permeability. If the current is 0, the magnetizing field strength, H, is 0, i.e. we're from a horizontal standpoint, we're in the middle of the curve. If H equals 0, then the resulting magnetic flux density is 0 in an ideal material. So therefore, you would be at the center of the curve horizontally. However, in a real material, if you look at the middle axis where H equals 0, you'll see that there is a remnant flux density. There's a field that remains at that point in time as if a current were still flowing. It's not, but it basically, that's the magnetic domains remaining partially aligned with each other. Okay. Note that as H goes left and right, you can see the arrows. The B does not retrace its curve coming back. Therefore, there's energy lost. And the energy lost in one loop equals the area inside the curve that's being traced, and it's called hysteresis loss. It's separate from eddy current loss. It's separate from the winding I squared R loss, okay? So if you're worried about heating in transformers, this is something you have to think about. Less driving reduces the loop area and the losses per loop. If you look at the little curve down in the lower left, you'll see that these things are being driven at different flux levels, as indicated by the little key in there. Like 0.2 Teslas is a tiny little circle, and 1.4 Teslas is a very large circle. So it depends on how hard you drive it. Note that is very, very important. If you want to have a much more efficient and cooler transformer or inductor, make sure you're not driving it as hard as you can up to saturation. Most people who start designing inductors or transformers start designing them to make them as small as possible. That's not necessarily a good thing. Make them a little bit larger. We'll see before that you don't have to make them see in just a moment that you don't have to make them that much larger. Okay, if you're going to make an inductor, you have to add a gap because a perfect magnetic path would never allow any current to flow because the inductance would be too high, okay? So to do that, we have to add a gap, and when that happens, you'll see that the BH curve, which is shown in blue and red in the sort of middle at the bottom, when you introduce an air gap, it actually flattens out. It sort of stretches right and left so that there's more current flowing left and right and left. The loss area stays about the same. But now all of a sudden you can drive it and not get anywhere near. You can store energy in it, and you can get the energy back out. In the lower right, you'll see a diagram showing the magnetic flux lines where there's a gap in the core, and you can see that the magnetic flux lines that are in the core actually bulge out right at the gap. And if the gap is significant, it's going to tend to be, it can fringe out substantially. If that gap is very, very small, it won't do that. So be aware that if you want to make sure nothing couples to that. Let's take a look at what we might use chokes for. They're used for many things, but let's assume a power amplifier chain is one of them. Let's say I have 3 amplifiers running off a power supply and amplifying a signal, say in a radio source. Now the last amplifier in particular probably has to drive a fairly large signal, and so it's going to be drawing current on and off as it needed to drive the output. Now the power supply has some impedance in it, and also there's some impedance between the power supply and that amplifier. So as that current draw changes and that impedance is there, there's going to be a flux. There's going to be a voltage develop, a delta V, and when that happens, you're going to see that the power supply rejection ratio of the op-amp is what's keeping that from actually getting into the signal. Well, at the very early stage, it may turn out that you have an adequate one and you don't need to worry about it. But gain 1 times gain 2 times gain 3 through 3 stages can be huge. If it's huge, you can get to the place where there's so much gain that the power supply rejection ratio of the first op-amp is insufficient to prevent it. This actually occurs quite often in high amplification change in communication equipments. So what do you do to make that go away? Well, you put a filter in line with each power supply. Sometimes just throwing a capacitor at each op-amp will help, but sometimes it's not enough. So I've drawn a pi filter here, and the goal is to try to say, let's make it to where the rejection from the last op-amp into the power supply line coupled with the rejection from the supply line into the first one gives us a double shot at reducing it, and we've pegged those inductors down at both ends, so we have an excellent rejection. This brings up another thought. If you're going to have a pi filter or some kind of filtering between your power supply and the other circuitry that it's powering, you kind of ask, okay, we'll have to throw some kind of an inductor in there, because this is a typical design problem. But if you go and have this tested for EMI, they're going to put some noise on the power supply side and says, is this going to disrupt what happens in your circuitry? Or they're going to put noise from your circuitry and see if that, or measure what's coming out and see if that actually makes it back out to the power supply. That's emissions. So we have susceptibility one way and emissions the other. But you always ask yourself, well, okay, I put this inductor in there, but do I need 2 capacitors, or should the capacitor be on the front or the back, or what? So let's talk about that for a moment. What do the caps really do? Well, a cap establishes a low impedance for high frequencies. So why would you want to do that? Take the top example. If you have a power supply that's high impedance, far away or noisy, then that's not a good thing to be starting with, sticking into your inductor. But if you establish that capacitor right at the inductor, you've established a low impedance point. Similarly, if your circuitry is high impedance, far away, or noisy, or sensitive to anything that might be coming in, you've got to peg it down. So if you put another capacitor right on the other end of that inductor, you're actually stabilizing it there. You're defining it near zero impedance to high frequencies at that point, and hence that filter can do its work. Now, in the second line, you can see that if your power supply is low impedance and it's very nearby and it's very quiet, probably because it has capacitors right in its output stage, well, if the inductor's right there, you probably don't need to put another capacitor in there. You can omit that one. Similarly, in the third line, if the circuitry you're driving is very robust, doesn't care much about noise, it's very quiet, it's very near the filter, and it's also very low impedance, then there's no real reason to have another capacitor on the output side. Well, it turns out if they're both bad, then sometimes it's best to put a capacitor on both sides, and you can also add a second inductor or so that you can also block what's in the ground line from going back and forth. Ideally, you'd make them a common mode, and that's a topic beyond what we want to discuss today, but common mode rejection is very good. Just remember that if you do that, the the ground on the left and the ground on the right are not exactly the same signal, so don't treat them as if they are. Let's look at a choke. A choke has a Q to it that's pretty low because a choke is designed to be a lossy inductor. Here's a typical example I got off of just one that I could find. You can see the part number there if you want to look it up yourself. Q of 10. So what does a Q of 10 really mean? Well, Q is equal to 2 pi times the energy stored in the inductor divided by the energy per cycle loss. If you go out and do that calculation for a Q of 10, you find out that 63% of the energy is lost per cycle. That's a whopping big amount. 63% of the energy is lost per cycle. That would not make a very good switching power supply. Chokes are not the same as inductors. They're designed to be lossy. Also, they have self-resonant frequencies. Of course, there's some intrinsic capacitance inside because they have pins and wires, and there's interwiring capacitance, etc. We'll look at how much in just a minute. Note that at the self-resonant frequency, this thing changes from being inductive to capacitive, and these frequencies may be well low than what you're trying to actually choke out. So beyond the self-resonant frequency, it'll become rapidly ineffective at filtering. So if I'm trying to filter out 300 megahertz, well, and I'm trying to use the largest one down at the bottom that has a self-resonant frequency of 4 megahertz, that's not going to work really well at all. If you do the calculations here, you'll find out that the capacitance in this case is very roughly about 4 picofarads. Fairly constant all the way through except down at the very lowest levels where it's defined as other things. Won't go into that, but it's a very low capacitance. It just has to do pretty much with the physical package. There's a DC resistance in the winding. Obviously, the higher the inductance, the more resistance there is. And so when you squirt your current through it, you're going to have resistive losses. Notice that there is also a rated max current in milliamps. If you combine those and take a look and see how much actual dissipation capability that relates to, you'll see it looks to be about 12 milliamps, all due to that I squared R loss. And it's a little different down at the very lower one because they're doing some things slightly differently. So how do they define rated current? Well, it's one of two things. Either when the temperature has risen to 20 degrees C, which is 1, or when the initial value of inductance has fallen by 10%. Aha! That second criteria is why it's a little bit different on the previous slide. It's a little bit higher power because you're in that regime as opposed to the temperature rising by 20%. The 20 degrees C would be an I squared R loss. So what happens at high H, at high magnetization flux, high ampere turns when you're putting a lot of current through this? Well, note that it starts to roll off. It's an inductance change, where this was graph of inductance, and note that the inductance actually starts to fall off. What's happening? How can it fall off? The number of turns hasn't changed. It's because the core is starting to saturate and you're actually getting a lower field at that point in time. You're driving it beyond its limits. Okay, note that as expected from 1/2 Li squared, the energy equation, note that for 10 times the current, the inductance drops by 100 times. So you got to be careful not just saying that, oh, this one works, let's just get the next larger size. You may not be able to support the current. One of these inductors will look inductive at low frequencies, but once you get to the self-resonant frequency, they turn around and they look capacitive, and all the curves start falling off again. If they fall off enough, you won't be able to filter what you need. Okay, and those frequencies again are calculated by 1/2 pi square root of LC, and you can look up the L and you can find the C, and there it is. You can calculate it. Notice the peakiness in the one that has the most inductance. It still has fairly low resistance, but since it has an L and a C and not much R, it gets peaky. That can cause problems for you because it might actually cause your circuitry to go and resonate. Look at this choke. It resonates and has a nice high impedance at 6.5 megahertz, and so it probably can deal with EMI nicely up to 10 megahertz or something. But what about at a gigahertz? At a gigahertz, it might only exhibit 10 ohms impedance and be wholly ineffective at blocking anything at all. So in some cases where you need to have a very wide frequency range or high current or other things, you may need to decide to actually have 2 chokes in series to accomplish your goal across the frequency range in question. Let's change gears a little bit. Let's look briefly at at a wire. Up above, you see a diagram of a wire charged positive and or a wire charged negative. They're not supposed to be in close proximity. That's not what it's indicating. But if you charge a wire either way, you'll see that it basically has an electric field emanating out from it. Since there is a permittivity of free space, that means that since there's a field, there's some energy. If there's some energy because of the charge that's gone in there, because of a current, that means you have that it has given it energy. Therefore, the E field comes about as a result of putting the charge in there, and so you have capacitance. A wire by itself has capacitance per unit length, even if it's out in the middle of free space. Similarly, if you have a wire in the middle of free space and you send current through it, that creates an H field around it, and that H field contains certain amount of energy based on the permeability of free space. So it stores energy. Well, since it varies with the current, that means that it has an inductance. So a wire in free space has both capacitances to infinity and inductance per unit length. If you walk through the signal, you'll see that the first charging of capacitors takes time before the voltage goes up on the first node to start there to be a voltage across the inductor, which causes the current to flow in the next capacitors, etc. down the line. It takes time to do that. You could say it's also doing a low-pass filtering, but that's because you're just drawing it as lumped elements. When the C's tend to 0 and the L tends to 0, and you do it with calculus, you'll see that goes away, and ideally it looks just like a delay. Hence, propagation speed in a wire is less than the speed of light. Okay, so a wire by itself will slow down a signal. Now, how does that affect us? Well, in PCBs, we have to worry about the propagation speed, and that's a whole part of it. There's several other things that go with those same fields. If I have a trace and there's a current through it, and it has a magnetic field, and if that field is changing, the magnetic field lines are changing. If there's a trace close by, some of those field lines will cut through that trace. If they cut through that trace and are changing, now I have a d phi dt. I have a changing magnetic flux, and they will induce a voltage into the second trace. Are there any other devices that do such a thing? Well, yes, there are. There's a transformer. So it's a loosely coupled transformer, but it is a coupled transformer based on the mutual coupling. So understand that traces, a pair of traces in a PC board side by side are a transformer. How do you get the energy down? Well, there's various ways you do that. We'll talk about that in a moment. Similarly, if you have two traces, there's some capacitance between them. This one we're more familiar with. And if there's a dV/dt on the wire, that one wire is changing in voltage, that will inject charge through the capacitor into the second wire, and that second wire then has this dI/dt, a changing current going through it, because I equals the mutual capacitance times dV/dt. Okay. Again, tracers close. How do you decrease this mutual coupling? There are four major techniques. First, number one, take the aggressor wave shape at the source and filter it or reshape it so that it doesn't have any more dV/dt or any more dI/dt than necessary when it makes it to the end. I.e., throw away the bad energy that you don't need to get the signal to its destination up front. Second, you can separate the traces far apart so that the aggressors and victims have very little coupling between them. Okay. Third, you can add shielding. You can add a Faraday shield between the two in the form of a ground plane that's stitched, or another plane, put them on opposite sides of a plane, etc., or a grounding trace. Or you can, for magnetic fields, you can actually put a piece of mu metal between things, but that's very hard to do on a PCB. Filtering, you can say, well, when the filter gets near its destination, the one that's the victim, let's try to filter it to throw away any bad influences that have gotten onto it. Generally not a good idea. The one you really have the most control over and you need to think about almost always is separation. When you design your printed circuit board, keep these signals away from each other. Figure out who they are and where they are. Figure out your aggressors and your victims, and make sure they can be routed far apart from each other. That's the one you have the most control over. And it requires you to make your PC board slightly larger than you would have otherwise. So don't let the size of the PC board be your driving factor. Let the quality of your product be the driving factor. Inductor losses, there are three major sources. The first is a resistance. There's winding resistance, and so when current goes back and forth through it, it creates an IR drop and heat. Okay. The second is that there's a hysteresis loss we talked about before in the core, and every time you traverse the loop, it creates heat. So you want to shrink that loop if you're trying to keep heating down, keep the inductor losses down. The third one is that when you change the B field in a coil, then that tends to change the magnetic field. When you change the current in a coil, it changes the B field. The B field changes the magnetic material and induces eddy currents in the core, resulting in I-squared losses of currents circulating in the core. Those are the three major sources of heat. So if you have a magnetic device that's running hot, those are the three suspect things that you need to reduce. One last thing I'd like to leave you with is the winding area core product. Power is given by the equation seen in the upper left, where AEC is the cross-sectional area of the core, KT is a topology of how it's used. I won't go into that. Bmax is the max flux density in the magnetic material, F is the frequency, and DC is the current density in the wire. Note that KT, Bmax, and DC are typically run right at their max, and so you can't practically increase them by design. But it can be seen that power scales linearly with frequency. That's why people are always trying to jack the frequency up so that they can get more power through a smaller device. The thing I want you to see is that power also scales linearly with the area product, which is the winding area times the area of the core. The winding area is the amount of area that you fill with wire cross-sectionally, and the area of the core is the cross-sectional magnetic path area of the core. And together they go like the fourth power of the linear size, which means that if you have a device that's 2 by 2, it can handle 16 times the power of a device that's 1 by 1. So don't always go for the smallest device you can. There are other benefits beyond that, such as resistance and things going down and Bmax going down. But just understand that a slightly larger device can have a radical influence on decreasing that. So again, this is Jeff Condit. That's the material we have for today.